Welcome to the next in the series of short videos about noise in electronic circuits, this time looking at a real op-amp based amplifier. This is the circuit that we're going to be investigating. It's an inverting amplifier with a feedback resistor R2 and an input resistor R1. And as you'll see, there are 5 different noise sources to consider even in this quite simple circuit. Both of the resistors have a thermal noise associated with them, and the op-amp has its 3 noise sources, the input equivalent voltage noise and the 2 input equivalent current noises. This is about the simplest op-amp circuit I could think of, but it's complicated enough for one short video. We'll analyse it by taking each of these noise sources in turn. It's a similar idea to that of superposition. We work out what the output noise is corresponding to each one of the input noise sources in turn, and then combine them all to work out what the total output noise will be. We've got 5 to consider. First one, the input resistor, R1. Well, if you put into the circuit the equivalent noise associated with this input resistor here, this circuit looks like a standard inverting amplifier with an input of the noise voltage of this resistor. So the output is just going to be this noise multiplied by the gain of this stage, which is R2 over R1. It's an inverting amplifier, so strictly speaking the gain is minus R2 over R1, but we're dealing with RMS inputs here. So the fact that it inverts this input is really of no consequence at all. That's not going to affect the RMS value of the output. The RMS is the square root of the square of the noise voltage. It's always going to be a positive number. So we can just take the contribution of this noise source here, which is 4kT R1, multiply it by the gain of this stage, R2 over R1, and that gives us an expression for the output noise contributed by this source resistor R1. Next, R2. Now, if we consider the noise due to resistor R2, first of all, note that the action of the feedback of the op-amp is going to keep its 2 inputs at approximately the same voltage. Since the non-inverting input here is at ground, the op-amp will keep its inverting input at ground as well. That means there is no voltage across R1. It's at ground potential on both sides, which means there's no current flowing through R1, which means there's no current flowing through R2 either, because at the moment at least we're not considering the input currents into the op-amp. If there's no current through R2, there's no voltage across R2. The output voltage here, therefore, would just be this noise voltage here below ground. And since we're only interested in the RMS value, the RMS voltage at the output would just be equal to the value of this noise source here, and that's just 4kT R2. You'll notice it's not a function of R1. This noise doesn't get multiplied up by the gain of the amplifier, whereas the noise due to R1 does. Okay, that's 2 of the sources, 3 to go. First of all, the equivalent input current noise associated with the non-inverting input. Well, this doesn't have any effect on the output at all. All this does is drag a little bit of extra current in through the non-inverting input. But the non-inverting input is still at ground, which means that the inverting input will still be at ground as well, which means no current flowing through R1 and no current flowing through R2 and no voltage drop across either resistor, which means the output is just going to be at 0. This noise source in this particular circuit doesn't have any contribution to the output noise at all. However, the noise current associated with the inverting input does have an effect. How much of an effect? Well, first consider that the action of the op-amp is again going to be keeping its two inputs at the same voltage. The non-inverting input is at ground, so the inverting input is going to be at ground as well. That means there is no potential difference across R1, which means there is no current flowing through R1. So this noise current here must be flowing through R2. There's nowhere else it can come from if there's no current flowing through R1. And if there's a current of IN flowing through R2, then the potential difference across R2 from Ohm's law is just given by IN times R2. So that's the voltage across R2. This side of R2, however, is at ground, so this side of R2 must be IN times R2 below ground. So the noise contribution to the output there, the RMS noise contribution to the output noise voltage, is IN times R2. Again, the minus sign is irrelevant, because all we're interested in is the RMS noise. That just leaves us one noise source to go. This one, the equivalent input noise voltage of the op-amp. Well, if we look at that circuit, it's actually exactly the same form as a non-inverting amplifier with an input of En and a gain of 1 plus R2 over R1. So we can determine the output noise of this circuit very easily. It's just the equivalent input noise voltage of the op-amp times the gain of this non-inverting configuration, 1 plus R2 over R1. We've now got our 5 contributions. All we need to do is combine them. And the thing we have to remember when we're combining them is that when you add independent noise sources, you have to add their powers, not their amplitudes. So we take these individual noise voltages, N1, N2, N3, N4 and N5, square them to get the powers, add up the powers, take the square root of that, and that would give us N, the final noise at the output of this inverting op-amp circuit. Next time we'll put some numbers in and see which one of these contributions is the most significant and which ones of them we can neglect.